Hi, welcome to Chemical Reactions Review Part 2. My name is Dr. English, and today what we're going to do is further continue our review of chemical reactions by specifically looking at different types of chemical reactions. The last part of the chemical reactions review will look at what drives a reaction. So today specifically we're going to look at an overview of synthesis reactions, an overview of decomposition reactions, an overview of single replacement reactions, and finally looking at double replacement reactions and how they're formed. So let's look at a synthesis reaction first. And the word synthesis really means to synthesize something, to bring something together. This is also known as direct combination, or combination reactions. I've heard all three used interchangeably. Now in the New York State Core, they specifically use the term synthesis. Don't be misled. It's the same type of thing if you're talking about direct combination or combination. And the general formula for a synthesis reaction is two or more simple reactants come together to form a more complex single product. You'll need to be able to recognize these reactions but not predict the products. So the symbolic form of this is A plus B yields AB. So simple reactants, more complex product. A real-life example of this might be sodium metal plus chlorine gas gives you sodium chloride, whether it's written out in a word equation or written out symbolically as we see here. And here's our pictorial view of the solid sodium metal, chlorine gas making table salt, sodium chloride. One thing to note here, a synthesis reaction is not an addition reaction. An addition reaction is very specific to organic chemistry, and that's when you have some type of hydrocarbon adding in typically either a diatomic hydrogen or halogen of some sort. Please make sure that you can differentiate between a synthesis reaction, which occurs with more ionic compounds or inorganic compounds, and an addition reaction, which is a more organic-based reaction. Now let's talk about decomposition reactions. The general definition of a decomposition reaction is a reaction in which you have a single compound broken down into two or more smaller, less complex compounds or elements. This is the opposite of our synthesis reaction. Again, similar to the synthesis reactions, you'll need to recognize these reactions, but you will not need to predict the products, unless you're translating from a word equation or something like that, but that's not very common on the Regents exam. So again, recognize, but you don't need to predict the products. So the symbolic form for this is if I had a more complex reactant such as AB broken down into A and B. So here's two examples of decomposition reactions. Here I have water breaking down into its elemental form of hydrogen and oxygen, probably through electrolysis, or calcium carbonate broken down into calcium oxide and carbon dioxide through a heating process. So the heating process here would break it down into more simpler substances from the original reactant of calcium carbonate. Now let's talk about single replacement reactions. When you're working with synthesis reactions and decomposition reactions, those you just need to be able to recognize, to look at and say, yes, I can categorize that as synthesis or I can categorize that as decomposition. With single replacement reactions, these are a little bit more involved. It'd be perfectly acceptable on the exam for them to give you all the parts of a single replacement reaction and ask what's the missing component, or to ask will this reaction happen or not. So a little bit more detail needs to be paid to these type of reactions. In these type of reactions, the reactants are almost always one free element, so a single symbol by itself or a diatomic, and one ionic compound. And the ionic compound will have the AQ symbol with it, meaning that it's dissolved in water. That's how you're going to recognize these reactions. So here's my two reactants. If I look at this in terms of a symbolic form, I have the A here, which is either my metal or my nonmetal by itself. I have BX representing my ionic compound. And what will happen here basically is that the A is going to come in and kick out the B. The B will then be the free element by itself. So if we watch this little animation here, the A is going to now hook up with the negative ion represented by X, and the B is going to be pushed out by itself. So literally it is a single replacement reaction. where you have something that's more active replacing something that's less active, as we see down here. So the more active element will replace the less active element. And this is where we get into table J, which is your activity series, which we're going to use in a minute. Now, this is important. When you're doing these types of reactions, note, metals are going to replace metals, and more active nonmetals are going to replace less active nonmetals. So let's look at a couple of examples. All right, so here's our first example. We have solid zinc plus silver nitrate. Will this reaction occur? The way to figure out whether or not this reaction will occur is to go to your table J and find the two metals that are involved. So here's zinc. Zinc is located right here, and silver is located way down here. Zinc is more active than silver, so zinc has the ability to replace anything below it, any element below it. But silver cannot replace the zinc. You can replace down, but you can't replace up. So what's going to happen here is that the zinc, because it's more active, is going to come in and kick out the silver. So will the reaction occur? Yes, yes it will. So the silver is going to get kicked out by itself. So pure silver metal right here, forming a solid. And then my other product. Now here's the important thing to do. Remember, when you're trying to figure out the new ionic compound that's formed, make sure that you write the correct formula. So I have Zn, and the charge on Zn is +2. I have NO3, which is nitrate, that's coming from table E. And what's going to happen here is that the Zn, the +2 for the Zn is going to come down here. The -1 is going to come down here. But remember the mantra, no positives, no negatives, no ones. So when we finally write this last product here, it's going to be Zn, parentheses, NO3, and parentheses, 2. And then if we wanted to go back really quick and balance this, we could say, all right, I have 2 NO3s, so I'm going to put a 2 in front of here. That gives me 2 AGs. I'm going to put a 2 in front of here. So 2 NO3s, 2 NO3s, 2 AGs, 2 AGs, 1 zinc, 1 zinc. It's balanced. Because in the end, it's going to bug you anyways if you don't balance it, so you might as well. Let's look at our next example here. Cu plus K2CO3. Now, can the Cu come in and kick out the potassium ion? Well, again, let's look at our elements. Where are they? So here's Cu. I'm going to highlight that in green. And K is way up here. So can Cu replace K? No. No, it cannot. No. Because the potassium ion is the more active metal. The copper is the less active metal. So you could just drop the copper into the potassium carbonate solution. Nothing's going to happen to the copper. So will this reaction happen? No. Not going to happen. Let's look at our last example here. I have solid aluminum being put in sulfuric acid, and I can say that this is sulfuric acid because it's H2SO4 in an aqueous solution. Can this happen? Can the aluminum come in and kick out the hydrogen? Now you may be like, wait, Dr. English. I thought you said that it's all metals over here and nonmetals over here, and hydrogen, the last time I looked, hydrogen was not a metal. This is very true, but remember, on these charts, you always want to look if they include a little asterisk or a double asterisk, because usually that's pretty important information. So if we look down here, it says activity series is based on the hydrogen standard. H2 is not a metal. They're specifically pointing that out. Let's look at where everything's located on this list. All right, aluminum is right here and hydrogen is right here. So again, although hydrogen is not a metal, it's part of the standard that's used to organize these metals in this activity series. So can aluminum replace the hydrogen? Yes, it can. Yes, it can. So that means that the hydrogen is going to get kicked out, and we're not going to represent hydrogen as just H. That's not stable. We want hydrogen represented as its diatomic. So H2 right here, and then the aluminum's going to come in, and once again we have to be really careful about the compound that we form. So I'm going to write Al plus 3, and then SO4 minus 2, and I can always look up the polyatomic of sulfate on my reference table E to double check my charges. and then I'm going to cross these down. So the 3 is going to come down here, the 2 is going to come down here, and again, no positives, no negatives, no 1s. So when I write out this formula, it's going to be AL with the 2 down here, parentheses, SO4, end parentheses, 3. Because I'm working with polyatomics here, I'm going to balance my polyatomics first. So if I look at this, I say, well, I have 3 SO4 ions over here, so 3 right here, so I'm going to put a 3 in front of this whole thing. So now I have 3 of these, I have 3 of these, and because I'm working with that, I'm going to go ahead and balance my hydrogens. So 3 times 2 gives me 6. So I need to get 6 hydrogens over here. So I'm going to put a 3 in front of here. So 3 times 2, that gives me 6. And I'm underlining as I go to make sure that I've accounted for everything. So the hydrogens are balanced, the sulfate ions are balanced. The only thing that's left over is the aluminum. I have 2 aluminum right here. So that means I need to throw a 2 in front of here. Everything is underlined, everything is balanced, and yes, this reaction will happen. And again, remember, this is a review here, so I'm not doing all that many examples, and I know I'm not doing an example with a nonmetal. In terms of how often we see these type of questions on the exam, it's much more common to get a metal replacing another metal than a nonmetal replacing a nonmetal. But you do want to take some time to go over and review that before the exam. Finally, let's talk about double replacement reactions. So what's happening in a double replacement reaction? Well, the easiest way for me to approach it when I teach my students this concept is to take the positive ions from the 2 reactant ionic compounds. So you're always going to start out with 2 ionic compounds, and you're going to separate them down in there to component ions, and then what you're going to do is you're going to switch the positive ions around so they go with the new negative ions. So switch with each other to form new compounds. So the positive ions from the 2 reactant ionic compounds are going to switch with each other, and we're going to form new compounds based upon this switch. These are identified by the presence of 2 compounds as reactants and 2 compounds as products, ionic compounds. Most double replacement reactions will not occur unless they're in an aqueous solution. We'll see that either the little aqueous symbols involved in the compound, or it's assumed if you're talking about a double replacement reaction. So the symbolic form here is AX plus BY. So what we're going to watch here is the location of the A and the B. When we see this happen, the A is now going to go with the Y and the B is now going to go with the X. The important thing here is that you have to remember back about how to write ionic formulas. It's the positive ion first and then the negative ion. When this happens, let's put the A over here, let's put the B here, and then we'll watch these two. So now the B is now with the X and the Y is now with the A. But it's always the positive ion first, then the negative ion. When you're doing double replacement reactions, the best thing that you can do is take it slowly. So if we look at this example right here, the first thing we're going to do is break up the 2 reactants into positive and negative ions. Now, if you're good at this, you don't need to do this step, but for those of us that make silly mistakes, it's never a bad idea. So if I look at my first reactant here, I know this is going to be Na plus 1 and carbonate, so CO3 minus 2, and again, I'll check that on table E. Then I'll look at my second reactant, Ag plus 1 and NO3 minus 1, again on table E. And what I'll do is I will basically say, all right, this Na is now going to go with the NO3, and this Ag plus 1 is now going to go with the carbonate. So when I write these over again here, I'm going to be really careful. So before I put them up here and I balance it, I'm going to say, all right, I have Na plus 1, I have NO3 minus 1. These positive and negative 1 are going to cancel each other out. So this is going to be NaNO3. And then plus, and now I'm going to look at my other compound that I'm going to form. Again, I'm going to list the positive ion first. So Ag plus 1 and CO3 minus 2. And again, I want to be really careful about this when I cross down my charges. The minus 2 is going to go down here. The plus 1 is going to go down here. So when I rewrite this formula up here, it's going to be Ag2CO3. The The big thing that you want to be careful with here is that you want to rewrite your products being really careful to write the new formulas. That's the thing that you really want to watch for. If I go back and I balance this really quickly, because it's always a good idea to balance it, again, I'm going to start out by looking at my polyatomics because they're prevalent here. 1 NO3, 1 NO3, so that's balanced. 1 CO3, 1 CO3, those are balanced. So now I'm going to look at my AGs and my NAs. Over here I have 2 Na, so I'm going to put a 2 here. So 2 NAs, but that's now messed with my nitrates. So 2 NAs, so really that means I have 2 nitrate polyatomics here. And now I've got to go back and put a 2 in front of here because the nitrate is located on this side. So the 2 distributes through, so now that's 2. So what have I done so far? Let's keep track of everything. 2 NO3s, 2 NO3s, that's balanced. 2 NAs, 2 NAs, that's balanced. CO3, still 1 CO3, still 1 CO3, so that's fine. So the last thing that's not underlined is the AG. So here's AG, and with that coefficient of 2, it means I have 2, and look, there's a subscripted 2 here, which means there's 2 AGs. Now that's balanced. So again, written my formulas correctly up here, I've balanced it, we're all good, the double replacement reaction is done. Let's look at 2 more examples just to round up this review. So I have BaClO3 Mg3PO4 2. First thing that I'm going to do is break these down into positive and negative ions. So Ba has a charge of +2, ClO3 is -1. I look at table E for that. I'm going over here and I have Mg +2 and then PO4 -3, and both of these polyatomics I can check on table E. So now I say to myself, all right, well, how's this going to work? Well, this positive ion right here is now going to go with the PO4, and this Mg +2 is now going to go with ClO3 -1. So I'm going to rewrite them over on this side with the ions next to each other so I can cross them down correctly. So I'll start with the Ba. So Ba +2, and that is PO4 -3. I'm going to cross these down. So when I rewrite this, this is Ba3 parentheses PO4 and then a 2 down here. So that's set up correctly. And then I look at my other ionic compound that I'm forming as a product, and again, you have to write the positive ion first. So I'm going to write Mg +2, ClO3 -1, 1 there, cross these down, Mg, we're crossing a 1 down so I don't need to write anything, parentheses, ClO3, and then a 2 down here. Everything's crossed correctly, so I'm going to write it back up here for a minute. Ba3, PO4, 2, Mg, ClO3, 2. And the final thing that I'm going to do is I'm going to balance it really quickly, because if I balance it and the balancing works out, then most likely I've written everything correctly and we're good to go. So let's start with our polyatomics again here. ClO3, I have 2 of them here, so I'm going to put a 2 here. ClO3, I have 2 of them here. That's balanced. Let's go to my other polyatomic. PO4, I have 2 of those here. PO4, I have 2 of those here. Again, that's working out pretty well. But now I'm wondering about my BAs and my MGs. All right, let's start with the Mg. I have 3 MGs here. I only have 1 Mg over here, so now I have to put a 3 here, and yet again, like that other example, it's going to mess with my polyatomics because this 3 is going to distribute through. So 3 MGs, which really means I have 3 times 2, and that's a critical thing to remember. This 3 and this 2 are going to come together. We're going to multiply them. 3 times 2 gives me 6. Instead of now having just 2 ClO3s, I now have 6. So I have to go over here and say, all right, what do I need to do? I need to put a 3 in front of here. 3, because 3 times 2 is now going to give me 6. But now that affects my BAs. Let's go back, start over, look at everything one more time. 3 MGs, put a 3. 3 mgs, put a 3. That's balanced. Now let's go to the ClO3s. 3 times 2 gives me 6, that's balanced. 3 times 2, that gives me 6, that's balanced. We just balanced the BAs, so BA, I have 3 here, I have a 3 here, and now I'm just going to check my magnesiums one more time. 3 mgs, 3 mgs, everything's underlined, we're good to go. And that's a pretty complex one. You've got polyatomics going on, you've got a lot of things to pay attention to, so take your time with that one. Let's look at our last example. Ammonium hydroxide and lead 2 chloride. Now you've got to be really careful here because you have 2 polyatomics occurring. We're going to have NH4 plus 1, OH minus 1, PB plus 2 because I'm going to uncrisscross that, and Cl minus 1. I take my ammonium and now that's going to go with the chlorine, and I'm going to take my PB plus 2 and that's going to go with the hydroxide, and I'm going to again pair them up next to each other to make sure that I can crisscross them correctly. NH4 plus 1, and I'm going to put that with the Cl minus 1, and then the PB plus 2 and the OH minus 1. I'm going to cross these down, but plus 1 minus 1, those two just cancel out. That means I'm just going to rewrite it to NH4Cl, so that'll be my first product. And now I'm going to look at the PB. So this plus 2 is going to go down here. This minus 1 is going down here. And for the last time, no positives, no negatives, no ones. When I rewrite this one, it's going to be PB OH 2. And I could take these formulas and rewrite them up here. NH4Cl plus PB OH 2. And then again, the final thing that I need to do is balance this. So let's look at here. I'm going to go with polyatomics again. 1 NH4, 1 NH4. Let's go to the other polyatomic. 1 OH, 2 OHs. So let's balance that out. So there's 2 OHs, so I'm going to put a 2 in front of this whole thing. So 2 OHs, 2 hydroxides, but that now messed with my ammonium ions. So there's 2 ammonium ions here, so I'm going to put a 2 in front of here, which now means I have 2 chloride ions. But there's a subscripted 2 there, so there's 2 chloride ions here. And then finally, the last thing to underline is the PB. 1 PB, 1 PB. Hey, I'm balanced. I'm good. I'm done. Everything is written out correctly. Everything is balanced correctly. And there you go. In the next review session, what I'm going to talk about briefly is what drives these reactions. How do I know this is going to happen? What's going to make it go forward? Which sort of differentiates from the single replacement reactions. We can look at table J to figure that out, and we'll be able to look at a different table to figure out what's driving these reactions. So what did we learn in this review? Well, we went over synthesis reactions, we went over decomposition reactions, we looked at how to write and how to predict the products of a single replacement reaction, and finally we looked at the basic idea of double replacement reactions, but we're going to go into that in a little bit more detail in the next review. Need more help? Feel free to contact me, and again, I'm always looking for feedback. Have a great day.